Hello and welcome. In this video, we're going to be solving another very hard mechanics question. This is the 9709 October-November 22 exam paper. This is question 6. But before I jump into that, in the next 2-3 minutes, I'm going to show you how you can get all of mechanics syllabus explained to you thoroughly, solved, and how to master mechanics in literally a very small step. What I want to tell you is that I've made a course on Udemy. This course is designed to be an alternative to tuition. What do I mean by that? I mean that when I was your age, I used to pay huge amounts of money for tuitions. However, I didn't like that. So what I wanted to do is to create something that basically has everything you need for mechanics. This is a Excel and Cambridge course. It has literally every single topic, kinematics, explained and solved. So you will see me on exactly the same whiteboard I'm doing this video on, solving super tough questions, explaining everything thoroughly, start to finish. This is designed to be an alternative to tuition course. So it's everything you need for mechanics. And then at the end of the explanation chapters, you will have a past paper section where I solve both Cambridge and mechanics full past papers. And then after that, I have a summaries and keywords section which help you grasp and understand everything. This is a 16 hours course. It's very, very useful. It's literally a gift. I will leave a link to it on the description and on the top right hand corner. Please feel free to go check it and email me for a discount on this course. Email me on the email in the link down below. Write in the subject Udemy mechanics course. All right, back to this question. Let's start by reading this question and then attempting to solve. So this question says figure 6.1 shows two particles A and B of masses 4 and 3 kilograms respectively, attached to the ends of a light inextensible string. Light means that tensions on both sides of the strings are equal. Tension throughout the whole string is equal. And inextensible means something that's very important, means that acceleration of both particles at the end of the string of the same string are equal. So accelerations are equal, velocities are also equal at the same instant of time, and if A moved 1 meter down, then B must move 1 meter up. This is all shown by the word inextensible. These are very, very important keywords, and again, it's highlighted in my course in the keywords and modeling section, but not only for this, for everything, for chapters like momentum, kinematics, and everything. So again, feel free to check it out. So it's an inextensible string that passes over a small smooth pulley. So the pulley is massless and no friction in the pulley. The pulley is fixed at the top of a plane, which is inclined at an angle of 30 degrees to the horizontal. A hangs freely below the pulley and B is on an inclined plane. The string is taut and the section of the string between B and pulley is parallel to the line of greatest slope. It's given that the plane is rough. This plane is rough. That means that there will be some friction and the particles are in limiting equilibrium. Okay, limiting equilibrium is a very important idea. Let me tell you what is limiting equilibrium. Limiting equilibrium, it means that we are in equilibrium. Okay, so there is no acceleration. The key word for equilibrium is that acceleration is equal to 0. That means that sigma f equals ma is basically equal to 0. So sigma f is equal to 0. And that implies that forces are balanced. Forces balance and cancel each other. There is no net force, basically. This is the word equilibrium. Okay, what about limiting equilibrium? Limiting equilibrium is just, it means that we are almost about to move, almost about to break equilibrium. The forces are balanced exactly the same. If anything happens, if I move B a little bit or give it a little bit of a push, or we're going to go out of equilibrium. Okay, this word limiting equilibrium directly relates to friction. Let me give you a small example. Let's say we have a box over here. You're pushing 10 newtons to the right and the box is not moving. Okay, so you're pushing 10 newtons to the right and the box is not moving. That means that there is a friction force on the other side that's exactly 10, right? Because the box is not moving. If this side was greater, then it will start to accelerate to the right. Okay, let's say you brought your friend, and now both of you are moving the box with 15 newtons, okay? And then you find that the box is still not moving. That means that the friction now became 15, right? Now, what about you increased a little bit more? You increased to, let's say, 16, and the box started to move, okay? That means that friction has to be less than 16 because we started to move, right? So friction increased from 10 to 15, okay, but couldn't increase to 16. Why? Because 15 Newton is called the, let's say, the maximum friction. Friction cannot increase infinitely. It has a maximum limit, and this limit is given by mu, which is the coefficient of friction, multiply r, which is the normal force to the plane, okay? So the idea of limiting equilibrium means that we are not 16 and 15, the thing is not moving, however we are in limiting equilibrium, so that means that the friction reached its maximum, and this maximum is balancing whatever force is there. That's why we're not moving. However, the word limiting means that friction is maximum friction. So in other words, it basically tells you in simpler and straightforward words that whenever you see limiting equilibrium, it means that the friction force is equal to mu times r. Okay? This is a very important concept. Okay, so it says that the particles are in limiting equilibrium. Find the coefficient of friction between B and the plane. So as any other question, we start by drawing a free body diagram for both particles. So let's start with A. A is going to have a weight force acting downwards, and it's going to be mass times acceleration of gravity. G for Cambridge is 10 meter per second squared. And what other forces are acting on A? We're going to have a tension upwards. Okay? That's it. Do we have any acceleration for A? No, because we're in limiting equilibrium. So that's it. And that implies that the tension force is going to balance the 4G force, so they are basically equal. Now, let's do the free body diagram for B. It's going to have a weight force acting downwards with a magnitude of 3G. It's going to have a tension force, which is going to be equal to this tension force because it's a light string. And we're going to have a normal force or a reaction force that's perpendicular to the plane. Let's call it R. Okay? That's it. Now, we always resolve the forces that we need to resolve. Our x-axis here is this direction parallel to the plane, and the y-axis is this direction, which is perpendicular to the plane. Any forces that are completely in x or in y doesn't need resolving. Any force that is in between will need resolving. So tension is clearly in the x direction. Okay. R, or reaction force, is clearly in the y direction. By the way, it could be in the opposite x direction. So if I had an imaginary force here called L, for example, I would not resolve it because it's still in the x direction. It's just negative. Okay. So the only force that needs resolving is the weight, because it's literally like this. It's not in fully in x or fully in y or fully in x. So we need to basically pressure it to be in x and y. So we basically get two components. So we divide this force into two components, one in the x direction, or first y direction, and another one in the x direction. Okay, and I will get those components. First of all, if this angle is 30, this is clearly 90. So this angle, using the triangles, sum of angles of triangle add up to 180. So 90 plus 30, that is 120. 180 minus that, so this angle is 60 degrees. And I know that this direction and that direction are perpendicular because that's the x and y direction. So if this is 60, this angle must be 30 as well. Okay? So we established that this angle is the same as this angle, 30. To get the y component, I'm going to start from my force that I want to resolve. If I'm moving into my angle, into the 30 degrees, this one, into the angle to get the components, it's then cosine. So it's 3g cosine 30. Then if I'm moving away from my angle, away from this 30 degrees, then it's going to be sine. So this component here is 3g sine 30. Now I completely resolved both particles. So what I should do now is start by writing my sigma f equals ma equations. First of all, I'm going to take the particle A, and I'm going to, for A, x is the horizontal direction, y is the vertical direction, right? Because it makes sense, all the forces are vertical, so this is the axis that makes sense. However, in the inclined plane, always take the axis as x is going to be the inclined plane direction and y is the perpendicular to the plane direction. So for A, I'm going to get sigma Fy, so I'm resolving or getting Newton's second law in the y direction. This should equal to ma. Since I don't have any acceleration, this is going to equal 0. That means that forces are balanced, so I can straight away put in that the upwards forces, which is tension, are going to equal the downward forces, which are 4g, and this is my first equation. Second thing, I'm going to take particle B. I'm going to do sigma Fy as well. Y of B is this direction. So I'm going to resolve forces or do Newton's second law for this direction, perpendicular to the plane. It's also equal to ma. A is 0, so it's equal to 0. So again, forces are balanced. So the forces in one direction, the R, forces in the positive y direction, R, are going to equal the forces in the, this is 30, in the negative y direction, so, or in the opposite direction, is going to be equal to 3g cosine 30. Now, first of all, I forgot another force over here that I need to add to B. There's tension, normal, weight, and since it's a rough plane, I will have a friction force. Okay, so where is this friction force going to act? 4 kilograms. 4 kilograms is greater than 3 kilograms, so it makes sense that this whole thing would want to fall downwards. Okay, if we're in limiting equilibrium, we're not falling, however, we're tending to fall downwards. So B is about to move up and A is about to move down. If B is about to move up, then the friction should act in this direction. And since it's limiting equilibrium, what is the value of friction? Just like what we established here, is going to be equal to mu multiply R. Okay, so now let's do B sigma Fx equal 0 as well. So the forces up the plane are going to equal the forces down the plane. So tension is going to equal 3g sine 30 plus mu R. Okay, what is R? I got R previously, 3g cosine 30. That's why I like to resolve in the y direction first. So mu times R, which is 3g cosine 30, and I know that mu is I know that tension is 4g, so I can replace this as 4g equals 3 times 10 is 30, sine 30 is half, so 30 times half is basically 15, plus mu times 3g cosine 30. So if I want mu, I'm going to move this 15 to the other side and divide by 3g cosine 30 equals mu. And if I put this in the calculator, taking g as 10, so 4 times 10 minus 15 over 3 times 10 cosine 30, that's going to give me a mu value of 0.962. And this is the proper answer for part A, and this is how to get all the 6 marks. Okay? Now, the harder part, okay, is part B, which is a very, very interesting idea that's very useful for you to understand. This question tells you it's given instead that the plane is smooth. So the plane is now smooth. So do we have friction or not? We don't have friction, right? And the particles are released from rest when the difference in the vertical heights of the particles is 1. So the difference between the vertical heights of those two particles is 1 meter. Okay, this is interesting. Use an energy method to find the speed of the particles at the instant when the particles are at the same horizontal method. Whenever it says an energy method, this equation should come in your mind. I use this form of the equation, which I feel is very, very easy. It goes, it's the work energy principle equation basically. It's work in to the system minus work out of the system equals change in kinetic energy of the system plus change in gravitational potential energy of the system. The word system means the system that you chose. You can choose A alone as your system, so you're gonna do everything for A, so the change in kinetic energy for A, change in gravitational potential energy for A alone, and then you can choose B as your system, so you do another equation, everything for B, or there is a smarter, better way to choose both particles as one single system, and I'll show you how to do that in this question. This is a very, very important idea. But before we do that, you need to understand what each term means. Work in is basically any external force, okay, multiplied distance. So because work is force times distance, the which force? Any external force that gives energy into the system. What do I mean? I mean it's force like pulling A down, it gives it energy, it accelerates it. Force like pushing A down, forces that basically give A some energy, okay? Work out is the other way around. It's forces, external forces that take away energy from the system. Like what? Like friction, air resistance, and so on. Okay, here you might tell me, okay, A has a weight component, so 4g, so this weight component is going to be added in the work in. I tell you, theoretically you are right. However, in this form of the equation, work in is any external force, okay, other than the weight, not the weight. Why not the weight? Because I will include the weight part, or the role that the weight plays in the delta GPE. So for this question, any external force that is not weight, okay? So let's say they're falling down, B, let's say we're talking about B now. The tension here, if my system is B alone, then the work in is going to be the tension, because this tension is an external force that's pulling B upwards, giving it some energy. So it's going to be tension multiply the distance that B moved. If my system is B alone, okay? However, when we choose the system as the whole, both particles, there is a change. I will tell you about it, but this is the way that I like to do it. Choosing the whole system, it's way easier. It's just a one-time shot, basically, to solve the question. Anyways, we spoke about the work energy principle equation. It's very important for you to understand it. Now, let's see how can we apply it. First of all, before choosing work in, work out, what I will do is, let me think about what do I mean by the vertical distance difference is 1 meter, and the question wants use an energy method to find the speed of the particles at the instant when the particles are at the same horizontal level. Okay, using this drawing over here, let's try to draw. Same horizontal level means, let's say this is the same horizontal level. Let's say when both particles are here. So A is here now and B is here. That means that they're both on the same horizontal level. So what happens here? You need to understand something. This is, let's say this is 1 meter, right? And this is so this distance is 1 meter. Let me, I don't know where is this. I don't know where is this point. Okay, how far is it from the baseline, or how far is it from here? I don't know. So what I'm gonna do is I'm gonna call this distance. Okay, I'm gonna call it h. Okay, this is the distance, the vertical distance that B will go up to be in that position that we don't know where is it. I'm just going to call it h. I'm not going to give it a number. If I know it, I'd call it 0.8 meters, but since I don't know it, I'll just name it h. Okay, let's think about it. If B moved h upwards, so if this distance is h and this whole distance is 1, so how much is this distance? It's basically the whole distance subtracting h. So the distance that A should move vertically, which is this one, should be 1 minus h, basically, right? That is the interesting part, okay? The second interesting part is that you need to understand, since the string is inextensible, remember it told us that the string is inextensible, the amount that A moved, if A moved 1 meter downwards, then B should move 1 meter upwards. If A moved 2 meters downward, then B is going to move 2 meters up the plane. Okay, so this is going to help us a lot. How? That means that the distance that A moved, which is this 1 minus h, should equal the distance that B moved up, right? Let's call this distance x, for example, okay? So let's do a small triangle for B. I know that B is going to move a vertical distance of h as agreed, okay? I know that along the plane, B is going to move a distance x, and I know that this is 30 degrees. So if I want a relationship between h and x, I'm going to do sine 30 going to equal opposite, which is h, over hypotenuse, which is x, right? So I can get this distance, which should be equal to this distance. I can get it in terms of x and in terms of h. So x is going to equal from here. H, I'm going to multiply this over there and divide by sine 30. So x is going to equal h over sine 30. So h over sine 30 is basically half, so it's h over 0.5. So h over 0.5 is basically 2h, okay? So x is 2h, right? So this is equal to 2h. And I said that if A moved a distance downward, B must move the same equivalent distance upward. So if A moved 1 minus h, this 1 minus h must be equal to x, which is basically 2h, right? And from here, I can actually get this distance that moved, h. I'm going to move this to the other side. 1 equals 3h, because it's going to be, I'm going to add h both sides. 2 plus 1 is 3. So h is basically 1 over 3 meters, right? So this is the interesting part that I wanted you to take care of. So let's write it here, that h is equal to 1 over 3 meter. And now let's write the work energy equation for the whole system. I'm going to use the whole system, okay? The whole system. So when taking the whole system, you need to neglect tensions, okay? There's going to be a tension here and a tension there. You need to neglect tensions. When taking the whole system, you will neglect tensions, okay? But sir, you told me for B, let's erase a little bit. You told me that for B, since T is a pulling force for B, it should be in the work in, right? It should be, work in is going to be the tension times whatever distance that B moved upwards, right? Correct. This is if we're taking the B alone as a system. So if we're taking, we are free to do that. If we're taking B alone as a system, then work in is going to be tension multiply D, okay, minus work out for B. Is there any external force? Is there any resistance to B, blah, blah, blah? No, it's going to be 0, right? That is for B, and that's going to equal change in kinetic energy of B plus blah, 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 okay? And for A, similarly, here tension, A is moving downwards. So tension is going to be a force that's resisting me. So it's going to be in the work out, okay? So the work in for A, I don't have any external forces acting on A that's going to cause work in. So work in is 0 for A, minus work out is going to be tension times distance. This is if I'm taking A alone and B alone. Yes, you should include them in work in and work out. But here what I'm going to use is I'm going to take not B alone and not A alone as my system. I'm going to take the whole system and apply this equation for the whole system. When I take the whole system, then neglect tensions. Neglect any work done by the tensile forces, okay? So over here, to take the whole system, what I'm going to do, let me write this. H equal 1 over 3 meters. Let me write it, let's say, okay, let's just write it over here. So the whole system, is there any external force that is not tension, because we're neglecting tension, and not weight, because we said weight, we're going to account for it in GPE, that is causing any pulling or pushing or any giving any energy to my system? No. A is going to fall downwards, B is going to move upwards. There is no any external force that's going to cause this type of work. So work in is going to be 0 for the whole system. Let me ask you, is there any external force that's going to cause resistance to the system that is not tension? Why not tension? Because we're neglecting tension. Is there any resistive force? Is there any friction? No, the plane is smooth, so nothing. So work out is also 0. And that is going to equal the change in kinetic energy for both particles. So the change in kinetic energy for A is going to be half times mass of A, which is 4, times the velocity final of A, this is the thing that we need to get, so let's call it V squared, minus the velocity initial for A, which is, it started from rest, so it's 0 squared. This is for A. I need to add to that the change in kinetic energy for B, because I'm taking the whole system. So plus half into mass of B is 3. Velocity final of B is going to be the same as the velocity final of A, so I'm going to call it, it's the same V as well. And since it started from rest, so minus 0 squared. And then I will need to add the changing gravitational potential energy for A. So it's going to be mgh, so 4 times g times h. How much did A move? It moved 1 minus h, and I know that h is 1 over 3, so 1 minus 1 over 3, okay, downwards. So 1 minus 1 over 3, that is 2 over 3. So it moved 2 over 3 meters downwards. So it's going to be negative 2 over 3 meters. Why negative? Because it moved downwards with respect to its starting position. Okay? Plus mg, so m for B is 3g. And what is the h for B? It basically moved this h, which is 1 over 3. And is it positive or negative? Yes, it should be positive, right? So mg h. And from this equation, I can just straight away solve for my velocity. So the left part is going to be just 0 equals half times 2, half times 4 is basically 2 times v squared plus 3 over 2 v squared plus 4 times 10 times negative 2 over 3 is negative 80 over 3 plus 3g times 1 over 3, this and this cancels, so it just becomes 10. So I'm going to have here 2 plus 3 over 2, that's going to be 7 over 2 v squared, this is 0, equal minus 80 over 3 plus 10 is basically minus 50 over 3. So I'm going to move this to the other side, becomes 50 over 3 equals 7 over 2 v squared. So I'm going to multiply both sides by 2 over 7, multiply 2 over 7. So this cancels, so I'm going to have v squared equal 50 over 3 times 2 over 7. That is going to be 100 over 21. Square root both sides to get v. So v is equal square root of 100 over 21. And v is going to equal 2.18 meter per second. And this is how I found v. See how it's just a simple equation, and choosing the correct system will help you eliminate more and more. Like we eliminated tension, we eliminated just basically tension because we chose the whole system, and we just had one singular equation where we solved for v and just got our answer. Very, very simple. If we chose both particles, so a different system for A and a separate system for B, we will have tensions in both equations, and then we will have to solve both equations simultaneously. It's going to give you the same correct answer at the end, however it's just more steps, so it's could be unnecessary. Anyways, I really hope that you enjoyed and found this video helpful. Please let me know in the comments section down below if you need anything else, if you have any suggestions. Don't forget to check the course, send me emails if you need anything. Thank you so much for watching, and have a nice day.